Yeah, thanks, George. It's a pleasure to be with you guys. Wish it could have been in person, but hey, it's good to see a community thriving and you guys getting together virtually, hybridly. So hopefully, I'll make it back to Austin one day to meet with you guys in person. But today we're going to talk about Apache Kafka. I entitled this, folks. This is Apache Kafka, and I'll get into why in a minute. This is like a developer's intro to Apache Kafka and event streaming. So just a quick intro about me. Professionally, I work at Confluent. I'm a senior developer advocate. I have 20 plus years of experience working with mainly applications and microservices on the JVM. I'm not a Python developer, but I play one from time to time. I'm North Carolina born and raised. I'm based in Raleigh with my wife and my daughters. And I point out, for diversity's sake, I like to point out my tribal citizenship. Just because there's not a lot of indigenous people in tech. So I always like to call that out. And yeah, I'm into all things outdoors when I'm not tethered to the keyboard. So today we're going to talk about Kafka, of course, where we've been, why we're here, where we are now. And to do that, we'll take a stroll down memory lane, looking at how we build applications. We will build an understanding of Kafka from the ground up, terminology and how those terms are related to one another, and how those terms allow Kafka to deliver on some pretty bold promises that it makes, some pretty bold claims that it makes. Excuse me. Then we'll talk about the developer interface a little bit. And then finally, we'll go over some of the other parts of the Kafka ecosystem. I'll also try, if we have some time, to show you guys some Python code that I hope you don't laugh at. That is a simple producer and consumer of events from Apache Kafka. Why the title of this talk came about? It's a story I heard from, ironically, from a pastor. He was talking about a time when the Green Bay Packers were coming back to training camp. You guys are in Texas. Football's a religion. I understand that. But the Green Bay Packers were returning to their training camp in 1961. They had just lost the NFL championship game to the Eagles by blowing a fourth quarter lead. And the coach of the Packers was the legendary Vince Lombardi. And the first day of training camp the next season, he stands up before this group of guys who had been playing football forever. And he just goes, "Gentlemen, this is a football." So he was going back to square one, the basics of everything, blocking, tackling, you name it. Just because they had been to the championship game the year before, they lost it. So they needed fundamentals. Must have worked because they won their season opener 37-0, and they won 5 of the next 7 NFL championships. I say all of that to say that fundamentals and basics are important no matter what it is that you're talking about. So when I think about where we've been in application development and how we've built applications in memoriam and where we are now in this microservice age, I like to revisit where we've been and start that stroll down memory lane, thinking about the monolith, the big code-based applications. And I compare them to the menu at the Cheesecake Factory. You guys are familiar with this fine American establishment where you can get cheesecake fusion egg rolls, and you can get the pasta dish of your choice, or a burger or whatever. And the menu is like 38 pages long and it weighs 2 pounds. And they do a lot of things. They do a lot of things pretty well, but they don't do anything great. And that reminds me of the monolith. It does a lot of things, but it was complex. You could end up with a French fry in your spaghetti because things were complex. There was a lot of things going on in the kitchen. With the monolith, things are complex. Testing is cumbersome. There's a wide blast radius if something goes wrong in these monolithic applications. They specialize in nothing. They do a lot of things, but they don't really specialize in any one thing. They send emails. They service REST requests. They persist data. They just do a lot of things. So at some point, we decided we needed to be more agile, both our processes and our applications. We went from this monolithic approach to breaking things down into microservices, and these microservices had specializations. And with those specializations, we could divide up the work and do parallel work streams, and because we defined these service contracts and these bounded contexts within these microservices. So the email service did its thing, and the auditing service did its thing, and the order service and the inventory service, they did their things. They all talked over interfaces, but these interfaces were often implemented in REST or RPC or something like that, and we created all these point-to-point endpoints, all these point-to-point integrations, rather. Most of the time over synchronous request-response coupling. And that led us to this infamous spaghetti plot where we've distributed the monolith, but we have this complex dependency graph over some protocol like REST or RPC. And when I think of the monolith, I still think of things, the way we stored the data in the monolith is we traditionally were thinking about the state of things. We were thinking about nouns, the state of an entity at a specific point in time. So we stored that thing with its state. But a millisecond after we queried for that thing in that and got that state of that thing, something could have changed about that thing. The state could have changed. After all, people are using our applications, and there are millions of new devices coming online every single day. So the state's always changing. Life's happening. Events are happening. Verbs are happening. Trains are moving. For instance, users are changing their address. Items are flowing in and out of shopping carts. People are purchasing things in their shopping carts. So if we think of our applications or our microservices in terms of verbs, we can start to answer some other more complex questions about our data rather than just the state of it right now. We can start performing some analytics and doing some predictive analysis on this data, like based on events X, Y, and Z, that I know that there's trends towards these other events that may happen, or I can start suggesting to my users or algorithmically suggesting to my users what they should buy if they put those two USB cables in their cart. So this is my dollar store definition of the event-driven architecture. This is my discount definition of what being event-driven means. And if we're going event-driven, we have some core requirements of whatever infrastructure we use for that event-driven architecture. We need high throughput to be able to deliver data with low latencies. We need a scalable platform to scale production clusters up to meet the demands of our users, upwards of trillions of events per day and petabytes of data. We need permanent durable storage for that data. And we need high availability across cloud availability zones, across geographic regions. Kafka ticks these boxes. And here's how it does that. So here's the definition of Kafka straight out of the box from the ASF, the Apache Software Foundation, is that Kafka is a distributed event streaming platform used for high performance data pipelines, streaming analytics, data integration, and mission critical applications. Kafka is the de facto event streaming platform today. And we're going to go into why Kafka can say those things by building up our understanding of Kafka terminology. So let's start with that terminology. At the heart of Kafka is this notion of an immutable log. That immutable log is called a topic. Topics live on a server known as a broker. An application can create an instance of a producer to write data to a Kafka topic. And we can configure those producers to know how and where to send events to Kafka. There's tons of configuration objects that are used to optimize the way you send data to Kafka. We'll get into some of those in a bit. But you're using those knobs or those settings to determine, based on the type of your data, the the mission criticality of your data and the volume of your data, what you want to tune for. You can tune for performance. You may want to tune for delivery guarantees and durability. And there's trade-offs there. For instance, if you're just writing syslogs to Kafka, your persistence and durability of a syslog is a lot less important than that of financial transactions or a ledger that I'm building in Kafka, right? So there are client APIs and SDKs for multiple languages for Kafka, Java, all the JVM applications you can imagine. There's JVM implementation there. There's client libraries for Python, Go, .NET, JavaScript, and so forth. So when we put an event on a Kafka topic, that event is being produced by our producer, and that event is assigned a number, as you can see right there. This is a monotonically increasing number called an offset. And this is just the logical position of that event within that topic. And it's append only. This is an immutable log. Events are append only. I can't go back in and make an alteration to event number one. I may create another event that looks like event number one and append that to the log. And my consuming applications, which we'll get into later, may compensate for that. But I'm not editing any point in this log. So we're building a foundation here of terms. And so the terms we talked about here on this slide are a broker, which is the server that your data lives on, a topic, which is that immutable log, your producer, which sends data to Kafka, and offset, which is the monotonically increasing position of the events in a Kafka topic. What does an event look like? When a producer creates an event, that event consists of three parts. You have headers. Headers are optional. Think of headers as metadata about the event. It's useful for things like tracing, routing, auditing, logging. You have the event has a key. That key is some identifying information about the event. Say if we're persisting users to Kafka, we're sending user events to Kafka. Maybe we use the user ID as the key to those events that we send there. And that key is going to come into play a little bit later on when we talk about the durability and scalability of Kafka. So just remember our terms as we go along. The value of an event is the body of that event. This is the meat and potatoes of what happened, what occurred to an entity, what action was taken upon that entity, or what action are we requesting to be taken on a certain piece of data. So again, terms, we're building them up here. Terms that we learned here are the parts of an event, which are the key, the headers, and the value. We're good so far? All right. When a producer sends data to Kafka, the data is stored on Kafka as just bytes. It's not, you can't open up a Kafka file on your broker that is where the data is persisted on the Kafka broker and just start reading your data. It's just serializing byte data down there. And this is for efficiency. Because the data is immutable, you wouldn't really want somebody going in there and vimming a file and updating your log, right? So client libraries have to provide the producer with a way to serialize data to Kafka, both the key and the value part of that event. And to do that, client libraries provide this serializer abstraction to be used by those producers. There's a number of serializers that come right out of the box with Kafka, like byte array serializers or byte buffers, all the numeric types, strings, and vendors like Confluent, who offer other things to augment Kafka, also offer serialization and deserialization implementations for industry standard serialization libraries like Apache Avro or Protobuf or JSON. And on the slide here, you can see an example of an event, what an event might look like, the actual data within it. This is structured data. The header consists of the customer ID and a card ID. And then you can see that someone added this item, quantity of 1, to a cart. And the data is put into a Kafka event, and then when the producer serializes that, it's just bytes on the broker. So, excuse me, the new term we have here is serializers. Okay, so we have mutable data, serialized and ready to store in Kafka. We need to talk about scalability a little bit. And when we talk about scaling, we begin our discussion with partitions. A topic, term we used earlier, which is where the data is stored, can consist of one or more partitions. And producing applications are actually appending events to a partition of a topic. So here's our cart action topic that we've been looking at, and the producer sends an event to a partition. That one goes to partition 0 because it's a circle. Here I'm partitioning on shape. There's a very rudimentary way of showing you how we would send data to which partition. So that the circles go to partition 0. Here we are producing a triangle, and the serializer says send the triangles to partition 1. And again, we have a parallelogram or a rhombus or whatever you want to call this, and it's going to partition 2. So remember offsets? You saw that these offsets were increasing per partition. And as I said just earlier, when a producing application produces events to a topic, it's actually appending those to a partition of a topic. So an offset exists within the bounds of a partition of a topic. So there is a default implementation of partitioning. On the Java side, what happens in the Java clients is that the default partitioner will basically look at the metadata about the target topic, and it will take the key of the data that you're sending to it, hash code that, and then take that hash code and mod it by the number of modulo operation that by the number of partitions and decide which partition it goes to. If there is no key, then it uses sticky partitioning, which basically says I'm going to send a whole batch of events to one partition, and then the next batch I'll send to the next partition, and so forth. That behavior does exist in the Python client as well. It's not the default behavior. I'm trying to refresh myself on what the default behavior of the partitioner is, but there is an implementation of the partitioner in Python that will behave like the Java one as well. So like I said, your client library has an abstraction for partitioner. It has a default abstraction for a partitioner, and that's how data is routed to specific partitions of a topic. So the terms we learned here are partitions, how a Kafka topic scales, and a partitioner, which decides which partition the data is actually written to. We've been talking about scalability. Let's build on scalability and talk about durability, because this is all great on one machine, on one broker, but that doesn't give us any durability, because at some point we're going to encounter some kind of hardware failure, right? So remember brokers. Brokers, that's where our data lives. And we can configure more than one broker to live together in perfect harmony. And now we have a cluster. The partitions of a topic can then be distributed across the brokers in the cluster. So instead of all the partitions of this topic living on one server, now the partitions can be spread across the cluster. All of a sudden, this starts coming into focus that all of our data is not in one place. All of our eggs are not in one basket. But let's start thinking about distributing that partition data. The data is partitioned, and data is living on different servers, different brokers. But if we're really going to have durability to back up our scalability, we have to replicate this data. And the members of your cluster, the brokers in your cluster, are doing this behind the scenes using a process called replication. Replication is this inter-broker communication that the producer doesn't have to worry about. Behind the scenes, these brokers are sending data to each other to replicate the partitions of a topic. So each topic has what we call a replication factor. how many replicas of a partition will exist across the cluster. In this case, this topic 1 that we have here has a replication factor of 3. The light blue partitions that you see here, we call those the leader partitions. So when a producer or a consumer is communicating with a specific partition, they're going to communicate with the leader. The yellows are replicas, which are exact copies of the data from the leader partition. And these replicas are capable of serving requests if something should happen to the node that the leader is living on. So the terms we have here, we're still building this box of terms. These building blocks are our terms here. Replication and replication factor, a leader, and a replica. And specifically, I want to talk about in-sync replicas as we move along to the next section. Like I said, behind the scenes, there is a replication going on in between these brokers, and data's flowing to keep copies of these partitions up to date. Why? Because we're always going to encounter an issue. At some point, you're running Kafka, and one of your brokers is going to take a dirt nap. It's just going to go down. Failure is the only inevitable thing that we have in computing, right? But because we have a distributed, partitioned, replicated, immutable log, we have no worries here. Broker number 2 just went down, took a dirt nap. And that's fine because we've been replicating data. So broker 0 says, I know that broker 2 was the leader of partition 2, but I have a fully in-sync replica of partition 2 over here. So any requests that come in for partition 2 now start getting served by broker 0. And that gives you time to diagnose the issues. Yeah, death and taxes, I see that, that's pretty good. This gives you time to diagnose the issues of why the heck broker 2 went away. Maybe that can wait till in the morning if it's 2 o'clock in the morning and your operator got paged. Maybe that can wait till everybody comes in, or maybe we need to get something up and running now. So when we scale the cluster back to 3 nodes, back to 3 brokers, Kafka is going to do what's called a rebalance. It's going to start trying to redistribute the load again. And it's going to start replicating that data because that partition has a replication factor of 3. It's trying to get back to that. And as soon as that replication is caught up, then those other partitions are in-sync replicas again, and you're back to a steady state where if this happens again, you can still service all of your data. So we've got data in Kafka. We've serialized data to Kafka. It's scalable. It's durable. Data's there. Now what? We got to process this data, right? I mean, we just don't want to just store it. So a client application that is going to process your data from Kafka creates an instance of a consumer to process that data from your Kafka topic. So a consumer is configured with a deserializer implementation that's compatible to the serialization method that was used to write that data. So if a producer is writing strings or serializing strings to a topic, then the deserializer needs to know that those were strings and how to deserialize them, or if they're numerics, or if they're Avro or protobuf or whatever. So we have to have a deserializer implementation there. So what happens? So a consumer will grab event number 1, and then event number 2, and event number 3, and it's processing these events in the order that they were produced. It's not going to skip around in the log. It's going to process the events in the order that they were created. What about multiple partitions? Well, consumers process data from a single partition of a topic in the order that it was written to that partition. So a single consumer instance is going to do its best to consume data from all partitions of the topic. And it's going to try. And it may round robin this. If this is a single consumer, if our single consumer can meet our SLA needs for processing this data, everything's fine. But when the ingress of data is greater than the egress of data, meaning we're getting in more data than we're being able to process within our SLA, then we start seeing what's called consumer lag. And that consumer lag is the difference between the last offset that a consumer processed, and the latest event that was written to that partition. So every partition is going to have some kind of a lag to it. And if we can't keep up and we get too far behind, that's just a lot for a single consumer to handle. So how do we go about getting some type of parallel processing of our data? After all, we're storing it in a parallel, distributed, replicated, partitioned log, right? We should be able to do some kind of parallel partition, parallel processing. If we create instances of a consumer and we give them the same, when we configure that consumer, we give them the same group ID configuration property. Now we can start more instances of our consumer application with that same group ID. And there's a process that's going to be happening on the broker side or on the cluster side called consumer group coordination. So when I add more instances of my consumer applications with that same group ID, they start getting assigned different partitions. And as soon as there's a partition assigned to a member of that consumer group, new members of that consumer group come in and they go, well, partition 0 is already spoken for. Somebody's already processing it in our group. Partition 1, we already have a member of our group that's taking care of that. And the same for partition 2. So now we're doing true parallel processing on every partition of our Kafka topic. What happens if we start a fourth one? Well, that fourth one's just going to be sitting there idle until there is a consumer group rebalance. Perhaps one of those consumers goes offline, and that other consumer with the same group ID, he may get a partition assignment at that point. He may not. So in the meantime, he's going to be sitting around idle. Excuse me. So kind of think of this. The way I like to look at this, and I know there's some Kubernetes folks probably in the house here. So just assume that your consumer applications may be running in Kubernetes, and suppose you're running 4 pods, and maybe one of your pods periodically you may be using some kind of chaos monkey type thing or whatever to stop that pod and move it to another server in your Kubernetes cluster. Well, when that member of that consumer group goes away, that consumer group application stops, there's going to be a consumer group rebalance at that point to make sure that all the partitions are accounted for, and to make sure there's a consumer assigned to that partition, so that your consuming does not miss a beat, right? We still want to keep processing data, the same SLAs that we've had before. Let's go back to this topic of serialization on the producer side for just a minute. We talked about serializers, how we can serialize various data types, numerics, strings, byte arrays. But like our example from earlier, we typically would use some sort of a structured data model, a data model that has a schema with it. If we don't, then we're raising some serious concerns here, especially for our consumer applications. And this is where data contracts come into play and data integrity comes into play. And that's why we look at the use of these industry standard formats like Apache Avro, Protobuf, or JSON with schema to define a schema for our events that are coming into Kafka. Each of these industry standard formats like Avro, Protobuf, and JSON have a serializer implementation in almost any programming language you can think of: Python, Java, .NET, Go. And so that's just a part of the client API. I'll speak a little bit from the standpoint of Confluent and the ones that we maintain for Avro and Protobuf and JSON with schema. These serializers are what we call schema registry aware. So what is a schema registry? Schema registry is something that's going to allow us to start enforcing or being an arbiter or repository of our schema evolution. These schemas aren't static. We can define a schema today, and then requirements are going to come in, and we need to augment this data with more data. We need to add fields. We need to change a data format or what have you. When we talk about defining our data and data quality, you're going to hear a lot of talk, especially from Confluent, about this paradigm of shifting left. You've heard that term used in testing and maybe other things within software development, but shifting left within data streaming is to put the onus on the producing applications or as close to the source of the data as possible. This diagram that you see right here where I talk about data quality, you can see the top left-hand side, there's some actor that is the creator or the author or the maintainer of these schemas and would register these schemas with this schema registry. Your producer in the bottom left is going to be using a schema registry aware serialization or serializer that we talked about earlier, serializer implementation. That serializer is going to be using that same schema registry where the schemas are registered from the schema creator. And it's going to say, okay, so I want to serialize this cart action object with version 1 of the schema. So schema registry, give me version 1 of that schema. I'm going to use that when I serialize my data to Kafka. As a consumer, I have a schema registry aware deserializer as well. So when that deserializer implementation gets that data from Kafka, it's going to look at that data and grab that version indicator from the raw data that it got from Kafka, call the schema registry. It's configured to use that same exact schema registry. So everyone's singing from the same song sheet here. And it's going to say, okay, so give me version 1 of this schema that this data was obviously serialized with because it says it right here in the data. Then I can deserialize that at those Avro bytes and process that data. What also happens here with the schema registry is the schema registry is enforcing that the data that is produced to Kafka conforms to whatever schema evolution rules that we have set within the schema registry for that topic. So we've got Kafka. That's awesome. We did it. We're event driven. Yeah, we solved all the world's problems, right? Not really. It would seem that we need to get some of our data that we have outside of our applications into Kafka. So we may have a bunch of external systems, databases, CRM systems, or sales systems like, your Salesforces and your SAPs or whatever. That's data that belongs in your ecosystem that you may need to join or you may need to augment with the data that's coming from your applications. And that's where a tool like Kafka Connect comes into play. Kafka Connect is a tool for scalably and reliably streaming data between Apache Kafka and some external system. That system may be the source of that data, say something like I mentioned, Salesforce or SAP or Postgres or some other database or HTTP endpoint. If those are the sources, then Kafka is your destination. So all of these are built on the producers and consumers that we talked about earlier. So in this case, if we're sourcing data from a system, we're producing it to Kafka. If we're syncing data from Kafka to another system, then that connector is built on the consumer API. Kafka Connect has some features that will allow us to do this in a reliable way. It has a common framework for creating your own connectors. You can use one of the hundreds of open source or paid connectors that are within the ecosystem, or you can write your own using one of the simple APIs that are out there for building Kafka connectors. There is a REST interface to manage the configuration of your Kafka connectors, how they're set up, how they scale, and the endpoints that you would use, the authentication that you would use to get to these external systems. Connectors are distributed and scalable by default. And they're built on top of the existing group management protocols like I talked about earlier for consumer group management and so forth. And this is really a good way of bridging that gap between streaming and batch data systems, because some of these systems that you see, some of these icons that you see here, they deal primarily in batch. But we can periodically go get that data from Kafka or periodically write that data from Kafka into these systems. But everything else within our ecosystem is just dealing with data as if it were always streaming. And so that implementation is pushed out to the edge into these actual connector implementations so that everything within our ecosystem where we're dealing with our real-time data, real-time events, we deal with that in a streaming fashion. So if there's data from other systems and data from my applications and microservices, I need to process those streams of data. Let's go back to our noun verb analogy from earlier. And traditionally, on the left here, you can see, traditionally we've done active queries on passive data. What does that mean? So we've had this data at rest, and we traditionally did these joins and transforms and things of that nature on that data on demand. And so how many of you have ever had 4-letter words hurled at you by a DBA somewhere who says, we got all these quote unquote jobs hanging out here from this application, this microservice, because of all these, they run and explain on your SQL, and they blame you exactly for why the database is, going sideways the way it is. But with streaming, and with these event stream processing frameworks that I'm going to talk about, we can start thinking about running passive queries on active data. So as the data is coming in through these event streams, we're going to go ahead and read optimize that and store it in tables or streams that meet the needs, the materialized needs of our use cases, of our query use cases coming in. So we're read optimizing this data for usage by our application use cases. In the Java community, and I know I'm speaking to a bunch of Python people here, I'm sorry about this, but I wanted to make you aware of this. In the Java community, there's a library for this called Kafka Streams. Kafka Streams, again, is just a client library built on top of producers and consumers that allows you to do a lot of operations on data streams, transformations, filtering, routing, windowed aggregations, time windowed operations, joins, and things of that nature. And Kafka Streams is really a Kafka to Kafka library for doing things. So you may ingest data from multiple streams. Think of it as joining a couple tables in the database, but joining as that data is being produced, as that data is being written. You've probably seen the infamous word count examples when you look at stream processing frameworks. Everybody's got one. That's an example of an aggregation. Maybe there's some routing that you're doing where you're saying, okay, so these are my platinum customers, and I want to route all the transactions from my platinum customers over here because I'm going to send them some kind of incentive email later on and thank them for doing business with us. But that's being written to another Kafka topic. And then from that Kafka topic, this is the way you build your streaming data pipelines. You may say, all right, now that I've got this data on this data from my platinum users on this topic, I want to hook a Kafka connector to it and write this data to a database, or write it to Elasticsearch, or write it to some analytics engine where I can do further analytics on it. In the non-Java world, there's ways to do this. One of the more popular frameworks that you'll hear more about is Apache Flink. And there are Python libraries for Apache Flink. Primarily when people are working with Flink, it's either in Python or on the JVM. Spark Streaming is also there. Spark Streaming has Python APIs for it. Alpaca is a part of the Akka ecosystem, and I think that's JVM based as well. Apache Samza, I'm not sure how popular Samza still is, or if it's still around being maintained. It was created by our founder here at Confluent, so I'm not sure if it's still around. Each one of these frameworks has its own strengths and weaknesses. I won't get into those, but I would encourage you to do some experimentation, do bake-offs, do some compares and contrast of the features and how that fits into your way of operating, however you're delivering applications. I will take some questions, but I did want to pop this up here real quick and leave it on the screen while we're doing questions. We're going to be in Austin next week for Current 2024, which is the data streaming event conference-wise in North America. Starts on Tuesday, September 17th. I'll be in town next week. I'm presenting this actual talk that I just gave. I'm actually presenting it next week. And we also have, I'm also part of the day 2 keynote with the rest of the DevRel team, where we'll be talking about the data streaming engineer and some tools for data stream engineering. So this QR code, if you're in Austin, will get you a free pass to Current. So feel free to whip your phone out right now, take a picture of this, scan the QR code if you'd like to come. I think this is like a $900 value, $1,000 value here. So coming out to Current, if you happen to come to Current next week and you see me at the Confluent booth, come by, introduce yourself. I'd love to meet some of you guys in person. And with that, I'll take some questions. I'll go to the chat and see if there are any questions.
Sandon, someone was asking about whether this presentation is available.
I can give you a PDF of it. I'll send it to.
Just put it online somewhere and give us the link to publish it.
Yeah, I can do that. I can do that.
And another question: you prepared some code, some Python code. Can you show it?
I did. You're exactly right. I sure did. So let's get out of here and present something else. But yeah, I'm going to show you guys a little bit of code. Are you seeing that? You seeing Python yet?
Yeah.
Okay. I don't know. My audio changes whenever I leave this window. Sorry. It's weird. It just has to do with where I'm at. Okay. So what we're looking at here is I think this is the producer application. This is a rudimentary application that is producing data to Apache Kafka serialized as Avro. So this main function that you see here takes in a topic, is serializing when you're using Apache Avro, you can serialize data as what they call specific or generic. And I choose the specific route for a couple of reasons, but one is because whenever you are deserializing that data, you can actually put some type safety into place here. Avro is one of these serialization libraries where you can actually take the schema and generate code from it. In Java, there's plenty of plugins for like Maven and Gradle that will allow you to create Java classes. In Python, there are pip packages, I think, that will allow you to run a command and generate, is it data classes in Python? Don't hold me to that.
There are data classes in Python.
Yeah, so let me show you this is the schema of this data. And this defines the structure of that data. This is a very simple user. User has a name, user has a favorite number, and he has a favorite color. Nothing fancy, right? So let's go to our producer. Within our producer class, get back to the bottom where I was here. So in our producer main, where was I? There we go. So I'm going to load the specific schema. I'm going to create a configuration for my schema registry in it. And so what I'm using here is Confluent Cloud. That's why you see these properties like CC props, and there's some authentication here that I use to get to the schema registry and to get to Apache Kafka as well. So I'm going to configure my schema registry client. I'm configuring my serializer. This is an Avro serializer that is schema registry aware. So it needs that schema registry client and how to communicate with that client. And I'm also giving it the schema that I loaded, this specific AVSC file, this Avro schema file. I'm giving it that schema. And I'm also giving it the structure of my data, which is in a dictionary. So what'll happen here with this serializer, it'll take this dictionary object that actually meets the same structure as my schema. So you can see right here, I'm taking this user class and I'm creating a dictionary with a name, favorite number, and a color. And I'm saying serialize this dictionary as Avro using this schema. Right? That's what I'm telling my producer to do. And so I'm just, for purposes of this demo, I've configured my producer here. For purposes of this demo, I just have a loop here that continues to create user objects and serialize them to Kafka, or send them to Kafka using that serializer. And I'm just using Python's faker library here to create these, right? So you can see I call produce on the producer that I created. I'm telling it what topic to write that data to. I'm telling it how to serialize the string, serialize the key rather, how to serialize the value, and then some delivery guarantees. This is a callback actually. On delivery, I want to call this delivery report function. It's basically going to just print something to my console. So what we're going to do is we're going to run that producer and let it run, and it's going to start writing some data to Kafka. While it's writing some data to Kafka, we're going to start looking at our consumer side of this. A lot of this you'll see is fairly the same. I load some of my configuration properties from a properties file. I did that because I didn't want to hard code all these all of my connection strings and my credentials and stuff and show them to you on the screen. But the same thing applies here though, but in the inverse. We create our schema registry client, and here we create a deserializer. And this deserializer takes our schema registry and our schema and tells us how to map from a dictionary back to our user object. So we configure our consumer. And instead of just running for a finite amount of time like we did with the producer, we're telling this consumer to just keep running and keep consuming data, because remember, data in a Kafka topic is an unbounded log of events. There is no last event. This data is going to keep flowing in from our applications. We don't know whether the 10th event is the last event or the 3 billionth event is the last event. We want to keep consuming this data. So if I run my consumer, you'll see that it's already caught up with the little bit of data that was out there from my producer, right? So let me run my producer again. And if I switch back over to my consumer, you'll see it's consuming that data. Still consuming this unbounded stream of data that's coming in and just writing it to the console log. It's a very simple consuming application. Okay.
And how do you can you go back to the imports and see how do you set this up?
Sure, yeah. Give me just a second. I'll put these AirPods up because it's bad. But anyway, are we in the consumer? No, I think we're in the producer.
I see Confluent Kafka.
Yeah, so let's go look at my I'll take you to my requirements.txt so you can see the libraries that I'm bringing in. So you see Confluent Kafka there. The reason I use Confluent Kafka is because of the serializer that I'm using. I'm using that Avro serializer, which is schema registry aware. That implementation is Confluent's schema registry aware Avro serializer. I'm sure there are others out there. Or you could just use Avro itself out of the box. But what the Confluent implementation does is it puts a version indicator in the raw bytes that are written to the Kafka topic. And the deserializer implementation that corresponds to that serializer actually goes out and looks for those bytes that determine the version, takes those, calls the schema registry, gets the right version of the schema to deserialize the rest of that event with. So that's why I use the Confluent one. Pay no attention to protobuf here. I think I just left that there because we're using Avro. And some of these others are just transitive dependencies, and then you can see the faker library that I use.
Yeah, I'm just asking. I just asked to see how do you actually interface. So Confluent Kafka is the main library that you're using here for consumer.
In this instance, yes, because I'm using the Avro serializer from Confluent. Now there are Kafka clients. If you're not using these schema registry client or these Avro or schema registry aware, Confluent schema registry aware classes, there are client APIs for Python that will just allow you to talk directly to Kafka outside of Confluent, just using open source Kafka. but I just used this one because I wanted to demonstrate the structured data with Avro.
Okay. Anyone has
So there's
any
your
more
importance.
questions?
I have a question. So
Yeah.
it's probably been more for your consumer though. You just keep it running, and that's usually how it goes 99% of the time is for us as well. But I have a question. Could you auto scale your consumer to 0 if there's no messages in the queue until there's like a certain threshold is reached? Is that like how difficult would that be? Because that's never an easy thing anywhere that I've noticed.
So if you auto scale to 0, you would never know when an event came in, right? Unless you had something that was doing monitoring and then started it. So like the Kubernetes example I gave, say if you scaled down to 0 pods of your consumer application, you would need some type of metrics monitoring system to say, oh, there's a lag. There's an event. And that's really not what event-driven architecture is all about. You'd want to have an instance of the consumer laying around or running somewhere that is always listening. Besides, if we take down all instances of a consumer group, then that consumer group is considered to be offline, and we don't know about its lag at all because it's just not there anymore. So if we shut down all the pods, then we would have a reason to be tracking its lag, because it's no longer a valid consumer group. So the typical paradigm here would be to, if you want to do true parallel processing, is to have at least as many instances of your consumer, or at least as many threads of your consuming application as you have partitions of that topic. So you're doing true parallel processing. But if your event volume ingress is such that you can have less than that number of partitions in the number of consumers that you have, members of the consumer group, and still keep up with your SLA guarantees, then just run one, and he's just going to round robin to the partitions and get different partition assignments over time. Does that answer your question?
Yeah, but I was wondering, like in more of like in a cloud run, you do like event driven, and they can like scale down to 0 until they have an event. I'm wondering if mimic some of that functionality here, because I know it's also some difficulty in Kubernetes, because you do need another application that's monitoring all your topics,
right,
and that something actually happened in that topic, and then to spin something up. Just curious, just out of curiosity.
One thing I did see in a past life, and this kind of goes beyond the scope of Kafka, but we had, in my previous job, we were running Kubernetes, and I'm trying to remember the name of the add-on to Kubernetes that we had in our Helm charts, to where we didn't start as many instances of the consumer application as there were partitions initially, but you could give this module in your Helm charts a consumer group ID that it monitored the consumer group lag for. And if that lag reached a certain threshold, it would spawn another pod. So you add a pod to your consuming applications, and that would help you get caught up on your consumer group lag. And over a certain amount of time, if your lag went down to a threshold, then it would shut down that single pod that it spun up, or a pod, to get you back to a state. So you would have like a min size for your number of pods, but you would also have a max. You could scale up to that max and scale back down. I'm sure every Kubernetes orchestrator out there, every Kubernetes implementation out there has something similar. I know EKS has it, but I know that there's some things you can add to it. I'm trying to think of the modules that we added. I can't remember right off the top of my head, but that's one pattern that I've seen. You wouldn't scale back to 0 consumers. That's because then you have nothing.
It's an anti-pattern, but I'm just like a personal project curious.
Unless you just periodically started one. Like if you said, okay, we're going to scale down to 0, but every 15 minutes I'm going to start one just to see what's going on. And if he doesn't get any action, then it's going to scale him back down to 0. But if you start seeing a lot of consumer group lag, maybe you scale back out to 5 or however many partitions you have so that you can catch up. And then if your traffic's bursty, right?
That makes sense?
Yeah. Just curious. Thanks.
Sandon, I want to bring it down a notch because we're showing things that are kind of theoretical. They're actually very applicative from the standpoint of view. But I want to take it a step back to show the bigger picture because we usually in this meetup we have beginners or people trying to get in, and all of this is a bit too much about their heads, but not
Gotcha.
always. So here, let's talk about applications where Apache Kafka is being used. Like, I don't know, if you have, cash register machines in some supermarkets, or let's say multiple supermarkets, and you need to drive the data into headquarters and process the whatever sales we're making in a restaurant or I don't know, chain of restaurants or whatever. Those are like one applications that I can think of where you have consumers of data and suppliers of data, banks,
Right.
where users make also transactions. But give examples of things that you're familiar with so people understand.
So there's the classic e-commerce example, right? Of where you have various microservices that make up an e-commerce system. You may have an inventory service. You may have an order fulfillment service, a shipping service, and payment processing, right? So the backbone of those is that they're all communicating over Kafka. They're all using events. You go back to my picture earlier where instead of having these point-to-point REST or RPC integrations, we're talking events. We're talking over Kafka as our messaging bus, as our event bus, as our central nervous system of things. So maybe if someone creates an order and they check out their shopping cart, an event gets sent to say, all right, so this is a checkout event. Here's the items in the checkout event, and here's the total. And here's their payment information. Payment system, go process this payment for me. And the payment system says, okay, I processed this. This order is now paid for. Now you're looking at your inventory and your order fulfillment systems to say, okay, I need to reserve the items that were in that cart that were purchased, and I need to earmark those for this order so that the shippers can grab them, so that the inventory people can actually physically grab them off the shelf and print the labels and ship everything. Think of Instacart. Instacart's probably one of the best examples of, I've heard it said before, like if you could go inside of a set of microservices and a broker, this is what's happening, right? If you go to their actual physical location, you'll see groceries coming down a conveyor belt, and based off of who made that order, they're being routed to different parts to be boxed together, different places to be boxed together into a shipment. Kafka ecosystems or event-driven ecosystems built on Kafka are very similar to that.
Okay, so Kafka kind of guarantees that the data never gets lost and there's enough capacity to handle all this data. And these are the things that basically provides you reliability that all the information comes and goes through and gets processed to some degree.
So you as an operator, that's where you come in, right? So if you're the one operating Kafka, you're the SRE on Kafka, you're the subject matter expert here and the site reliability engineer. You have to make some determinations. How long do I want to keep this data around? How much data what's my ingress of data? What's my volume? What's the size of these events? And that's going to determine how much disk space you need to store this data for however long you need to. Now, Kafka does have this feature called tiered storage, where you can, in theory, keep your data forever, right? So you can back your storage on the broker with object storage. So if you're in Amazon, say you're running Kafka on AWS, you could back it with S3 as an object store. And so you're only paying for your S3 volume and your replication to S3 and your communication to S3 at that point, along with your storage volume that is on the broker. So what happens in that case is that the hot data, or based on the age of the data and the size of the data, the hotter data is going to stay on the broker. The colder data or the older data is going to be relegated to object storage.
Okay. So basically, Kafka allows you all sorts of ways to manipulate with all the data that flows. You can save it. You can decide not to save it. You can save it for a while. And this is this is what the system is.
Kafka allows you to democratize that data, right? So you're putting this data in a centralized, well, not really centralized, but in a location where it can then be integrated with other streams of data. It can be utilized in conjunction with these other streams of data to get you better information about your data. So we talked about the situation of the cart action that we were looking at earlier in my example. That cart belonged to a user. Well, what can I glean about that user? Well, if my users are on another stream, on another topic, then I could use something like Flink or whatever to join the carts with the users and maybe get demographic information about the people who are buying USB cables, 6-foot USB cables, right? So that's where they start to come in.
Okay, and what about security? Can you say, oh, this consumer is allowed or not allowed? Is
right.
this put into Kafka?
So you can do security you can do what's called ACLs, access control lists. And you can use authentication using SASL or SSL and various means. That access control can be very fine-grained. It can be down to the topic level. So you can say for the user topic, only folks in this role can access this and provide them with the credentials to either read or write from that topic. So if I'm a producing application that writes to the user topic, you're going to give me the most fine-grained controls as possible so that I can write to that topic. You may not give those credentials to anybody else. You may not give that permission to any other application so that I am the microservice that is writing this user data to this topic. Now, there may be many consuming applications that need user data from that topic. So you would grant an ACL to several of those applications to only read data from the user topic, right? So you can specify read or write permissions. You can specify at this granular topic level how folks can access what data. So it's not just the Wild West, though. If it's in Kafka, everybody can see it.
Very nice. Any other questions by anyone?
Have you seen how this interfaces with Splunk? It sounds like the Connect tool helps configure that.
Splunk can be one of your sources, or one of your sinks, excuse me. It could probably be one of your sources as well. I'd have to go look and see what connectors are out there in the ecosystem.
It sounds like its strength is in analytics. So letting Kafka do the storage and then Splunk can do the analytics seems like a good partnership.
Could be, yeah. To tell you the truth, I think Splunk uses Kafka itself once you get to their side. It only makes sense that they would use something like that because of the volume of data that is ingressed into Splunk on a daily basis, right?
Well, they did develop their own process, but from what I researched, it's not nearly as powerful as Kafka. And I think that's known. Kafka, of course, is built for parallelism as well in real-time events, which Splunk is not quite at that speed.
Yeah. When you get to Splunk, you're basically doing analytics on the data that you sent to Splunk, right? So, yeah, you're trying to glean insights.
Yeah. Thank you.
No problem.
Okay. Any other questions or?
Cool.
It was very informative. Thank you. That was a
Thanks.
presentation.
Thanks. If you're in Austin next week, come to Current. I'll be there. Look forward to meeting some of you guys.
Yeah, thanks for that link too.
Yeah.
Yes.
All right.